Alrighty, here we go. Starting the stream again. Alright, welcome back. Today we're going to be doing Algebra 2 and Khan Academy and functions. And we're going to start inverses of functions today. So we have a little video to watch, and then we have a document to read. And then we'll go on from there.
Let's think about what functions really do, and then we'll think about the idea of an inverse of a function. So let's start with a pretty straightforward function. Let's say I have f of x is equal to 2x plus 4. And so if I take f of 2 is going to be equal to 2 times 2 plus 4, which is 4 plus 4, which is 8. I could take f of 3, which is 2 times 3 plus 4, which is equal to 10. Right? 6 plus 4. So let's think about it in a little bit more of an abstract sense. So there's a set of things that I can input into this function. You might already be familiar with that notion. It's the domain. The set of all of the things that I can input into that function. That is the domain. That is the domain. And in that domain, 2 is sitting there, 2 is there, you have 3 over there. Pretty much you could input any real number into this function. So this is going to be all reals, but we're making it a nice contained set here just to help you visualize it. Now, when you apply the function, let's think about what it means to take f of 2. We're inputting a number 2, and then the function is outputting the number 8. It is mapping us from 2 to 8. So let's make another set here of all of the possible values that my function can take on. All of the possible values that. Let's think about what functions really do, and then we'll think about the idea of outputting the number 8. It is mapping us from 2 to 8. So let's make another set here of all of the possible values that my function can take on. All of the possible values that my function can take on, and we can call that the range. There are more formal ways to talk about this, and there's a much more rigorous discussion of this later on, especially in the linear algebra playlist. But this is all the different values I can take on. So if I take the number 2 from our domain, I input it into the function, we're getting mapped to the number 8. So let me draw that out. So we're going from 2 to the number 8 right there. And it's being done by the function. The function is doing that mapping. That function is mapping us from 2 to 8. This right here, that is equal to f of 2. Same idea. You start with 3. 3 is being mapped. 3 is being mapped by the function to 10. To 10. It's creating an association. The function is mapping us from 3 to 10. Now, this raises an interesting question. Is there a way to get back from 8 to the 2? Or is there a way to go back from the 10 to the 3? Or is there some other function? Is there some other function? We can call that the inverse of f that'll take us back. Is there some other function that'll take us from 10 back to 3? We'll call that the inverse of f, and we'll use that as a notation. And it'll take us back from 10 to 3. Is there a way to do that? Is that that same inverse of f, will it take us back from, if we apply 8 to it, will that take us back to 2? Will the inverse of f, if we apply it to 8, will it take us back to 2? Now, all of this seems very abstract and difficult, but what you'll find is it's actually very easy to solve for this inverse of f. And I think once we solve for it, it'll make it clear what I'm talking about. That the function takes you from 2 to 8. The inverse will take us back from 8 to 2. So to think about that, let's just say y is equal to f of x. So let's say y is equal to f of x. So y is equal to f of x is equal to 2x plus 4. So I could write just y is equal to 2x plus 4. And this, once again, this is our function. You give me an x, it'll give me a y. But we want to go the other way around. We want to give you a y and get an x. So all we have to do is solve for x in terms of y. So let's do that. If we subtract 4 from both sides of this equation, let me switch colors. If we subtract 4 from both sides of this equation, we get y minus 4 is equal to 2x. And then if we divide both sides of this equation by 2, we get y over 2 minus 2, right? 4 divided by 2 is 2, is equal to x. Or if we just want to write it that way, we can just swap the sides. We get x is equal to 1 half y, same thing as y over 2, minus 2. So what we have here is a function of y that gives us an x, which is exactly what we wanted. We want a function of these values that map back to an x. So we could call this, we could say that this is equal to, I'll do it in that same color, this is equal to f inverse as a function of y. Or let me just write a little bit cleaner. We could say f inverse as a function of y. So we could have 10 or 8. So now the range is now the domain for f inverse. F inverse as a function of y is equal to 1 half y minus 2. So all we did is we started with our original function, y is equal to 2x plus 4. We solved for, over here we've solved for y in terms of x. Then we just do a little bit of algebra, solve for x in terms of y, and we say that that is our inverse as a function of y, which is right over here. And then if we, you could say this is, you can replace the y with an a, a b, an x, whatever you want to do. So then we can just rename the y as x. So if you put an x into this function, you would get f inverse of x is equal to 1 half x minus 2. So all you do, you solve for x, and then you swap the y and the x if you want to view it that way. That's the easiest way to think about it. And one thing I want to point out is what happens when you graph the function and the inverse. So let me just do a little quick and dirty graph right here. And then I'll do a bunch of examples of actually solving for inverses. But I really just wanted to give you the general idea. Function takes you from the domain of the range. The inverse will take you from that point back to the original value, if it exists. So if I were to graph these, so let me draw a little coordinate axis right here. Draw a little bit of a coordinate axis right there. This first function, 2x plus 4, its y-intercept is going to be 1, 2, 3, 4, just like that. And then its slope will look like this. It has a slope of 2. So it will, let's see, it'll look something like, the graph will look, let me make it a little bit neater than that. It'll look something like that. That's what that function looks like. What does this function look like? What does the inverse function look like as a function of x? Remember, we solved for x, and then we swapped the x and the y, essentially. We could say now that y is equal to f inverse of x. So we have a y-intercept of negative 2, 1, 2. And now the slope is 1 half. So the slope is 1 half. The slope looks like this. Let me see if I can draw it. The slope looks, or the line looks something like that. And what's the relationship here? I mean, these look kind of related. It looks like they're reflected about something. And it'll be a little bit more clear what they're reflected about if we draw the line y is equal to x. So the line y equals x looks like that. I'll do it as a dotted line. Right? The line y equals x looks something like that. That is the line y is equal to x. And you can see you have the function and its inverse. They're reflected about the line y is equal to x. And hopefully that makes sense here. Because over here on this line, let's take an easy example. Our function, when you take 0, so f of 0 is equal to 4. Or our function is mapping 0 to 4, right? The inverse function, if you take f inverse of 4, f inverse of 4 is equal to 0. Or the inverse function is mapping us from 4 to 0, which is exactly what we expected. The function takes us from the x to the y world, and then we swap it. We're swapping the x and the y when we take the inverse. And that's why it's reflected around y equals x. So this example that I just showed you right here, function takes you from 0 to 4. Maybe I should do that in the function color. So the function takes you from 0 to 4. That's the function. F of 0 is 4. You see that right there. So it goes from 0 to 4. And then the inverse takes us back from 4 to 0. So f inverse takes us back from 4 to 0. You saw that right there. When you evaluate 4 here, 1 half times 4 minus 2 is 0. The next couple of videos, we'll do a bunch of examples so you really understand how to solve these and able to do the exercises on our application for this.
Alright, so now we're gonna work on we're gonna read the document. So, inverse functions, in the most general sense, are functions that reverse each other. For example, here we see that the function f takes 1 to x, 2 to z, and 3 to y. So 1 to x, 2 to z, and 3 to y. Inverse of f, denoted by f to the negative first, reads as f inverse. So this is f inverse. We will reverse this mapping. Function f inverse takes x to 1, y to 3, and z to 2. So you can see it takes 1 to x, 2 to z, 3 to y up here. And then down here, the inverse takes x to 1, y to 3, and z to 2. So we just flip it around. Which of the following is a true statement? The domain and range of f are the same as the domain and range of f inverse. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. Well, if the domain and the range are the same for f and f inverse, they'd be like the same uh the same equations. So that couldn't be it because they are the inverse of each other. And the domain of f is the range of f inverse, and the range of f inverse is the domain of f inverse. See, that makes sense because for f, this is our domain. That's all real numbers, which is also the range for f inverse. And then the range for f is also the domain for f inverse. This one in yellow is the, yeah. So that's got to be our answer. Defining inverse functions. In general, if a function f takes a to b, and then the inverse function f inverse takes b to a, from this we have a formal definition of inverse functions. So a, put it into f and you get b, put it into f inverse and you get a again. So this is our definition for inverse functions right here. Let's dig further into this definition by working through a couple examples. Example 1, mapping diagram. Suppose H is defined by mapping diagram above. What is H inverse of 9? So if we look at this here, H, this is our domain and this is our range from these numbers. So if you put in 0, you get 7. If you put in 4, you get 3. If you put in 6, you get 9. If you put in 9, you get 12. So we want the inverse, H inverse of 9. Well, as we saw up here, the inverse would be if you flipped the 2 and drew the lines the other way, pointing back the other direction. So if we flipped the 2 and had the lines pointing back the other direction, 3 would turn into 4, 7 would turn into 0, and 9 would go into 6, and 12 would go into 9. So the H inverse of 9, well, if we flip them and draw the lines back, it would be 6. So we are given the information that H asks a question about function H inverse. Since inverse functions reverse each other, we need to reverse our thinking. Specifically, to find H inverse 9, we can find the input of H, whose output is 9. This is because H inverse 9 equals x. Then by definition, H of x equals 9. For the mapping diagram, we see that H of 6 equals 9, so H inverse of 9 equals 6. So this is the G, this is a map for G, and we want to find G inverse of 3. Well, we have to find something on this side, that we have to find 3 on this side, and then work backwards to find the number on the other side. So there's 3, we work backwards, and that's a -1. I'll just plug in -1, check, and we got it right, so we're going to move on. The graph, of the function g. This is the graph of the function g. Let's find g inverse of negative 7. So we'll look at how to find that. To find g inverse of negative 7, we can find the input of g that corresponds to the output of negative 7. This is because if g of inverse of negative 7 equals x, then by definition of inverses, g of x equals negative 7. From the graph, we see that negative 3 negative 3 here equals negative 7. So negative 3 along the x-axis equals negative 7 along the y-axis. From the graph we see, yep, and then therefore g inverse of negative 7 is negative 3. So what is h inverse of 4? Well, we gotta find 4 here on the y-axis. Oh no, on the x-axis. And then on the y-axis, that's 1. Yeah, so that should be 1 because in h of x, in our h of x, yeah. And that is incorrect. So to find h of inverse 4, we can find the input of h that corresponds to an output of 4. This is because if h inverse 4 equals x, then by definition h of x equals 4. From the graph, we can see that h of negative 2 equals 4. So what we need to find is h of x equals 4. Well, whatever is inside this parentheses in x, that's going to be the y. That's going to be the y-axis. So we want to find h of 4. So we need to find where the inverse would equal 4. From the graph, we see that h of negative 2 equals 4, so h inverse 4 equals negative 2. Yeah. So our answer would be negative 2, and we got it right. So just hide that. And given that f of x equals 3x minus 2, what is f inverse of 7? Well, we got to find what number would make this over here equal 7, right? So we'll put 7 over here. We'll just replace this side with 7. So if we take the 2, add it to the 7, that'd be 9. 9 divided by 3 is 3. So if we plug in 3 to this equation, we'll get 7. And if we plug in 7 to f negative inverse of f, we'll get 3. And that's correct. So graphical connection. The examples above have shown us the algebraic connection between a function and its inverse, but there are also graphical connections. Consider function f given in the graph in the table of values. We can reverse the inputs and outputs of function f to find the inputs and outputs of f inverse. So if a comma b is on the graph of y equals f of x, then b comma a will be on the graph of y equals f inverse x. These sorry, this gives us these graphs This gives us these graph and table values of f inverse x, of f inverse. So you see how they took the everything that was x over here and put it over here, and everything that was over here and put it over here. Sorry about that. Looking at the graphs together, we see that the graph of y equals f of x and the graph of y equals f inverse x are reflections across the line y equals x. This line right here, and they're both reflected over that. This will be true in general. A graph of a function and its inverse are reflections over the line y of x, y equals x. This is the graph of y equals h of x, which is the best choice for the graph y equals h inverse of x. We want to take this and flip it over this x equals y axis. Right along here. And one sec. So we're going to look, this one doesn't quite look right. It is sloped differently. And we kind of want something that's parallel reflection over this axis. So this isn't it. This one doesn't quite look right because it seems to be rotated way too much vertically. So that's not quite right. This one looks like it's about 2. So if we look at the actual numbers here, this is 2 below, this is -2 from 0.00. And this one right here is 2 above 0.00. And if we look here, this should, on 0.6, it's this point right here is 0.6. So the point up here on the other side of the y axis, y equals x axis. Sorry about that. So this should be our answer here, right? So we'll check, and we got it wrong. So if we draw a line from here to here, all the way through all of these, at about this point here, the line will go in this way. So we want to flip it across this point right here, right where it goes past this. So this one should be our answer, maybe. No. Alright, so I'm going to look at the explanation because having some trouble here. So if we reflect the original graph across the line y equals x, we get the following. So we do need to reflect it right across this point here. So we take it and we flip this end down and we take this end and put it up. So this would be B. And we'll check and we got it right. So the graph y equals h of x is a line segment, and it's okay to get them wrong as long as you're learning. Joining the points 5, 1, and 2, 7. Drag the endpoints of the solid segment below to graph y equals h inverse x. Oh, this is the one we move. Okay, so So it goes from 5 comma 1 to 2 comma 7. Well, this would be, if this is our input and this is our output, we could just flip them. So we want to go from 1 comma 5 to 7 comma 2, 7, right? And there we go, we got it right. And then our line would go right through the middle of them, and that would be our line in the middle. Why study inverses? It may seem arbitrary to be interested in inverse functions, but in fact we use them all the time. Consider that the equation c equals 5/9 f minus 32 can be used to convert temperature in degrees Fahrenheit to degrees Celsius. But suppose we want an equation that did the reverse, that converted temperatures in degrees Celsius to temperatures in degrees Fahrenheit. This describes the function f equals 9/5 c plus 32, or the inverse function. On a more basic level, we solve many equations in mathematics by isolating the variable. When we isolate the variable, we undo what is around it. In this way, we are using the idea of inverse functions to solve equations. So now we're going to watch a video.
You may by now be familiar.
And then we have another video, and then we'll be doing practice problems.
You may by now be familiar with the notion of evaluating a function at a particular value. So for example, if this table is our function definition, if someone were to say, well, what is f of -9? You'd say, okay, if we input -9 into our function, if x is -9, this table tells us that f of x is going to be equal to 5. And you might already have experience with doing composite functions, where you say f of, let's say actually f of -9 plus 1. So this is interesting. It seems very daunting, but you say, oh, well, we know what f of -9 is. This is going to be 5. So it's going to be f of 5 plus 1. So this is going to be equal to f of 6. And if we look at our table, f of 6 is equal to -7. So all of that is a review so far. But what I want to now do is start evaluating the inverse of functions. And this function f is invertible because it's a one-to-one mapping between the x's and the f of x's. No two x's map to the same f of x. And so this is an invertible function. So with that in mind, let's see if we can evaluate something like f inverse of 8. What is that going to be? And I encourage you to pause the video and try to think about it. All right.
So we want to find the f inverse of 8. Well, we could work through all of this, find like how we found f inverse of 9 equals 5. But if we wanted to find, so wait, one sec.
Invertible function. So with that in mind, let's see if we can evaluate something like f inverse of 8. What is that going to be? And I encourage you to pause the video and try to think about it.
What we could do to find is we could just look through f of x. We could find 8, and it should be 9. Or no, we're finding.
All right.
Never mind.
So f of x, just as a reminder of what functions do, f of x is going to map from this domain, from a value in its domain, to a corresponding value in the range. So this is what f does. So this is domain, and this right over here is going to be the range. Now f inverse, if you pass it the value in the range, it'll map it back to the corresponding value in the domain. But how do we think about it like this? Well, f inverse of 8, this is whatever maps to 8. So if this was 8, we have to say, well, what mapped to 8? Well, we see here f of 9 is 8. F of 9 is 8. So f inverse of 8 is going to be equal to, and actually we do this in that same color, is going to be equal to 9. And if it makes it easier, we can actually construct a table here. And this is actually what I probably would do just to make sure I'm not doing something strange, where I could say x and f inverse of x. And what I'd essentially do is I'd swap these two columns. So f of x goes from negative 9 to 5. F inverse of x is going to go from 5 to negative 9. All I did is I swapped these two. Now we're mapping from this to that. So f inverse of x is going to map from 7 to negative 7. Notice, instead of going from this, mapping from this thing to that thing, we're now going to map from that thing to that thing. So f inverse is going to map from 13 to 5. 13 to 5 is going to map from negative 7 to 6. Negative 7 to 6. It's going to map from 8 to 9. 8 to 9, and it's going to map from 12 to 11. From 12 to 11. So let's see, did I do that right? Yeah, it looks like I got all of, yep. So all I did is really I just swapped these columns. It's mapping, the f inverse maps from this column to that column. So I just swapped them out. So now it becomes a little bit clearer that way. And you see it right over here. F inverse of 8, if you input 8 into f inverse, you get 9. So now we can use that to start doing fancier things. We can evaluate something like f inverse of, actually let's evaluate this. Let's evaluate f of f inverse of, let's see, f of f inverse of 7. What is this going to be? Well, let's first evaluate f inverse of 7. F inverse of 7 maps from 7 to negative 7. Maps from 7 to negative 7. So this is going to be f of this stuff in here. We do it in yellow. This stuff in here, f inverse of 7, we see is negative 7. So it's going to be f of negative 7. And then to evaluate the function, well, f of negative 7, that's just going to be 7 again. And that makes complete sense. We essentially we mapped from 7, f inverse of 7 went from 7 to negative 7, and then evaluating the function of that went back to 7. So let's do one more of these, just to really feel comfortable with mapping back and forth between these two sets, between applying the function and the inverse of the function. So let's evaluate what, do it in purple, that wasn't purple, so it's going, let's try to evaluate f inverse of 13. Of f inverse of 13. What is that going to be? I encourage you to pause the video and try to figure it out. Well, what's f inverse of 13? Well, that's looking at this table right here. F inverse goes from 13 to 5. And you see it over here. F went from 5 to 13, so f inverse is going to go from 13 to 5. So this right over here, f inverse of 13 is just going to be 5. So this whole thing is the same thing as f inverse of 5. And f inverse of 5, well, f inverse goes from 5 to negative 9. So this is going to be equal to negative 9. Once again, f inverse goes from 5. F goes from negative 9 to 5, so f inverse is going to go from 5 to negative 9. So at first, when you start doing these kind of inverse and function and inverse of a function, it looks a little confusing. Hey, I'm going back and forth. But you just have to remember, a function maps from one set of numbers to another set of numbers, and the inverse of that function goes the other way. So if the function goes from 9 to 8, the inverse is going to go from 8 to 9. So one way to think about it is you just kind of switch these columns. Hopefully that clarifies more things than it confuses.
All right, we just have one more video to watch, and then we're going to do the practice problems.
This right over here is our understanding inverses of functions exercise on Khan Academy. And it's a good exercise to make sure you understand inverses of functions. And it's an interactive one where we can move this line around. And they tell us the graph of h of x is in green. So that's this dotted green line right over here. The graph of h of x is the green dashed line segment shown below. So that's this. Drag the endpoints of the segment below to graph h inverse of x. So there's a couple of ways to tackle it. Perhaps the simplest one is we say, okay, look, h of x, what does h of x map from and to? So h of x, this point shows that h of x, if you input negative 8 into h of x, h of negative 8 is 1. So it's mapping from negative 8 to 1. Well, the inverse of that then should map from 1 to negative 8. It should map from 1 to negative 8. So let's put that point on the graph of the inverse. And then let's go on the other end. So let me just move this a little bit out of the way. On the other end of h of x, we see that when you input 3 into h of x, when x is equal to 3, h of x is equal to negative 4. So this point shows us that it's mapping from 3 to negative 4. So the inverse of that would map from negative 4 to 3. So if you input negative 4, it should output 3. If you input negative 4, it should output 3. And since we took the two endpoints of this line, and we essentially found the inverse mapping of it, what I've just done here is I've graphed the inverse. And another way to think about the inverse is if you were to draw the line y equals x. So I don't have my little pen tool right here because I'm operating on a web page. But if you imagine the line y equals x, these things should be reflections around the line y equal x. Because one way to think about it is you're swapping the x's for the y's over here. And you see that. If you were to draw the line y equals x, these things, if you flipped it around the line y equals x, the green line, you would actually get the yellow line. This would flip over there, and this would flip over there. But either way, we're done. We have graphed h inverse of x.